In this video, we're going to talk about some of the different ways that we can collect data. Here are a couple of terms that we're going to use in discussing these methods. We will refer to variables as explanatory variables and response variables. In research, we wish to determine how varying the amount of an explanatory variable affects the value of a response variable. For example, let's say I'm trying to figure out if people who study more for a test get better grades. In this case, the number of hours studied for the test is the explanatory variable, and the grade on the test is the response variable, because I'm trying to see if changing the explanatory variable, meaning changing the number of hours studied, affects what happens to the response variable, the grade on the test. Here we're going to look at the difference between an observational study and a designed experiment. An observational study measures the value of the response variable without attempting to influence the value of either the response or explanatory variables. That is, in an observational study, the researcher observes the behavior of the individuals in the study without trying to influence the outcome of the study. If a researcher assigns the individuals in a study to a certain group, intentionally changes the value of the explanatory variable, and then records the value of the response variable for each group, the researcher is conducting a designed experiment. So in our example, we were talking about the relationship between studying for a test and how well you do on the test. So if you were going to do an observational study, you could go into a classroom and you could survey the students and you could ask each person how long they studied and what grade they got on the test. And you could try to analyze that data based on just the information that they told you. But you're not trying to change how much each person studied. If you're going to do a designed experiment, what you could do is you could take the class and you could divide them into groups. And you could say, Group A, you have to study for 2 hours. Group B, you study for 4 hours. Group C, you study for 6 hours. And then you see what happens with each group. That would be a designed experiment because you're intentionally changing the value of the explanatory variable. Whereas in the observational study, you are just observing what happens with different values of the explanatory variable without changing any of it yourself. Here's an example, and I want you to pay attention to what could potentially be some flaws in this observational study. Researchers wanted to determine the long-term benefits of the influenza vaccine on seniors aged 65 years and older. The researchers looked at records of over 36,000 seniors for 10 years. The seniors were divided into two groups. Group 1 were seniors who chose to get a flu vaccination shot, and Group 2 were seniors who chose not to get a flu vaccination shot. After observing the seniors for 10 years, it was determined that seniors who got flu shots are 27% less likely to be hospitalized for pneumonia or influenza and 48% less likely to die from pneumonia or influenza. Now, this is an observational study because they're not telling the seniors whether or not to get a flu vaccine. They're just looking at whether or not they got a flu vaccine based on their own decisions. But remember, I asked you to pay attention to what could potentially be some of the flaws in this observational study. And the flaws in this study is that there could be some confounding factors. So what are confounding? Confounding in a study occurs when the effect of two or more explanatory variables are not separated. Therefore, any relation that may exist between an explanatory variable and the response variable may be due to some other variable or variables not accounted for in the study. And we call those variables lurking variables. A lurking variable is an explanatory variable that was not considered in the study, but that affected the value of the response variable in the study. In addition, lurking variables are typically related to any explanatory variables considered in the study. Here are some lurking variables in the influenza study: age, health status, or mobility of the senior. So how are these lurking variables? Let's take age, for example. Seniors who are on the younger side, closer to 65, might be more likely to go out and get a flu shot, but they might also be less likely to be hospitalized or die if they do get the flu. So when we saw that seniors who got the flu shot were less likely to be hospitalized or die from the flu or pneumonia, it's possible, we don't know, that it was actually from the flu shot. It could be because those seniors were the younger of the seniors, whereas the seniors who were 90, 100, or older were less likely to get the flu shot, but also more likely to die if they got the flu, and the flu shot itself may have had nothing or little to do with it. So again, these are called lurking variables because they are other explanatory variables which can affect the response variable. And when this happens, it's called confounding. Now, you can account for these potential lurking variables in various statistical ways, but the authors of the study concluded that getting an influenza shot is associated with a lower risk of being hospitalized or dying from influenza. They didn't say it caused, because they were doing an observational study. And observational studies do not allow a researcher to claim causation, but only association. Now, we've talked about the fact that it's often difficult to do a study of the entire population, so we want to select a sample instead. But we want to make sure that we select a good sample. And by that, I mean a sample that we can statistically claim is somewhat representative of the population. One way to do that is with random sampling, which is the process of using chance to select individuals from a population to be included in the sample. If convenience is used to obtain a sample, the results of the survey are meaningless. What does that mean? Let's say you own an ice cream shop and you want to get a sense of if people like your ice cream. If instead of getting a random sampling of people, you survey your best 3 customers, you're not going to get a good sense of what the overall population thinks. We'll often use a small n to represent the size of a sample and a large N to represent the size of the entire population. Now, a sample of size small n from a population of size big N is obtained through simple random sampling if every possible sample of size small n has an equally likely chance of occurring. The sample is then called a simple random sample. Here are some methods of obtaining a simple random sample. The first is picking from a hat or a box or something, which is exactly what it sounds like. You could, for example, put the names of every member of your population down on a small slip of paper of equal size, put them in a hat, and draw out the number of individuals that you need for your sample. If you do this without replacement, it means that once you have drawn someone's name, you don't put it back in the hat. But if you do it with replacement, then even once you've drawn someone's name, you put it back in the hat again. With a random number generator and a random number table, what you want to do is you want to assign every member of your population to a number. Let's say there's 1,000 members in your population, so you would assign them each a number between 1 and 1,000. And you would use either a random number generator, which is kind of the more modern method, it uses a computer to generate random numbers, or a random number table, which was the preferred method before computers became so ubiquitous, which is basically a listing of random numbers. And you would basically go through the random number table, and let's say you wanted a sample of size 25 from a population of size 1,000. You would pick the first 25 numbers that were 1,000 or under. Another type of sample is called a stratified sample, and this is obtained by separating the population into homogeneous, non-overlapping groups called strata, and then obtaining a simple random sample from each stratum. The individuals with each stratum should be homogeneous or similar in some way. You would use this when you want to really make sure that you have a representative or representatives from each stratum. So for example, it's possible, not likely depending on your sample size and your population size, that if you take a simple random sample of your population, you will end up with all males. If you really want to make sure that your sample contains a certain number of males and a certain number of females, then you might want to use a stratified sample, where you take a simple random sample from the males and a simple random sample from the females and put them together to really make sure that you have males and females in your sample. A systematic sample is obtained by selecting every kth individual from the population. The first individual selected is a random number between 1 and k. So here's an example. A quality control engineer wants to obtain a systematic sample of 25 out of 1,000 bottles coming off a filling machine to verify the machine is working properly. Since 1,000 divided by 25 is 40, he wants to pull every 40th bottle off the shelf. He randomly chooses a bottle between the 1st and the 40th, so let's say he chooses the 23rd bottle, and from there he pulls every 40th bottle. So the next bottle he would pull would be number 63, and then number 103, etc. A cluster sample is obtained by selecting all the individuals within a randomly selected collection or group of individuals. So here, our individuals are already divided into clusters, and what we're going to do is we're just going to choose some of those clusters, and once we've chosen a cluster, we're going to take all the individuals within that cluster. As opposed to the stratified sample, where each strata is fairly homogeneous, with the cluster sample, the clusters themselves should be somewhat representative of the whole. So for example, a school administrator wants to obtain a sample of students in order to conduct a survey. Instead of picking students at random from the whole population, she randomly selects 10 classes and then administers the survey to all of the students in each of those 10 classes. So once the 10 classes out of, let's say, 50 classes are chosen, every single student in those classes is in the sample. So here's just a little visual to see all these different types of sampling. In simple random sampling, you just take from the population itself, you just choose individuals. With stratified sampling, you have these somewhat homogeneous strata. So I think if you can see here, these are all male and these are all female. So you choose some from the first stratum and some from the second stratum. With the systematic sampling, you randomly choose whether who you're going to start with. Let's say I start with number 2. But then, from there, I'm going to be very systematic. I'm going to take every third person. So I have 2, I have 5, I have 8, I have 11. Now with cluster sampling, we already have our individuals broken into clusters. See here, they're broken into clusters of 4. And I'm going to randomly select clusters. So I selected this 1, 2, 3, 4 cluster, and this one is 17, 18, 19, 20 cluster. But once I've selected those 2 clusters, all the individuals, 1, 2, 3, 4, 17, 18, 19, 20, are selected to be in my sample. As I said before, a convenient sample is one in which the individuals in the sample are the ones most easily obtained. Caution: any studies that use this type of sampling generally have results that are suspect. Results should be looked upon with extreme skepticism. Finally, a couple more definitions. A sampling bias means that the technique used to obtain the individuals to be in the sample tends to favor one part of the population over another. Undercoverage is one type of sampling bias. Undercoverage occurs when the proportion of one segment of the population is lower in a sample than it is in the population. For example, if 35% of your population is aged over 65, but only 5% of your sample is age 65 or older, then you have undercoverage of the senior population.